So this is about the mathematics of a soccer ball. And I'll start with a story 19 years ago. It's almost reminiscent, you know. When I came here for an interview, and the other Peter Hamburger, insisted that I go to Walmart, get a bathing suit, coming from Florida. For whatever reason, he thought that I have to go to a swimming pool in the hotel where I was staying. So I said, okay, well, I'll do that. And as I was going to Walmart on Coldwater, I had this small soccer ball for my interview talk. And I bought a big one. Okay?
Is this the same
So
one?
yes, no, that's not the same. That's brand new. Somewhere in my attic is the original one. So I will place it right here as a good prop. And I also got some other props, you know, having the Vice Chancellor here, being a vivid golfer, and since I was going to talk about how we are going to distribute, well, points on the sphere, so it was very, very reasonable to get that prop. Please return them to Carl after that, because I have no use for them. As you can see, they have these dimples, and that's more or less well distributing points on the sphere. Now, the problem is very easy in the plane. We have direction, we have order. If I want to distribute, say, 100 points on a circle, that is the unit sphere in the plane, I will just measure up 100th of the circumference and place the points. However, moving in 3D, we have no direction, we have no order, and the problem becomes very, very difficult. So difficult that we actually distinguish a whole bunch of interaction. We need a quantity, and I will be talking about potential energy. And we want to minimize, as Carl well pointed out, chemists and physicists, and nature, by the way, does want to minimize the energy, the potential energy of any system. And we will consider a system of points. So what are our motivations for studying these kinds of problems? Well, the first one came at the beginning of the 20th century. J.J. Thomson asked the question, well, how are we, imagine the electrons are interacting according to Coulomb law, how are we going to distribute them so that we have minimal energy? And that was a reasonable question. And here we see our first picture of the soccer ball. This is about 60 electrons, I guess, in equilibrium. So we need some kind of a model. Usually the way that we measure energy is with some all possible forces of interaction, and we will assume that each point has the same kind of charge, and then we are minimizing something that is the reciprocal and weighted to some power s. This is a parameter that we will talk about. When s goes to 0, actually this is a nice part of the talk, the derivative here, talking about mathematics, but more or less that problem gets minimizing the logarithmic kernel, which is because sum of logs is log of a product, that's really maximizing the product of all possible distances. So we vary the potential. We have a lot of different kinds of problems. And here are 32 and 122 electrons in equilibrium. Now you will see that around every electron there is a small cell that is the nearest neighbors on the sphere that are associated with this electron. You can think of these guys as the schools and the cells being the school districts. Having two of my colleagues here from math education is quite a nice interpretation of this kind of problem. So I am also optimizing school districts on a planet. Okay? Moving on, biology. Well, in 1930, Thomas, a Dutch botanist, studied distribution of orifices of pollen grain and asked the following question. Now, by the way, the orifices want to distribute themselves in a best possible way. That means that we want to cover the sphere as well as possible. So every little piece of that sphere wants to have orifices. And that is actually Thomas' problem. How do we maximize the minimum distance between these orifices? You don't want them to be very, very close. Okay, that's one way to actually consider minimization or optimization and well distribution of problems, of points on the sphere. Another interpretation for distributing these points is how do you place fuel depots on the planet, okay? So that you can drive with your truck or whatever to the fuel depot, get the gasoline and deliver it to the stations, all right? So you want to cover well all of these. You can think also of these are the satellites and their coverage. Now, that could be another related problem. If you want to cover the entire sphere, then you're talking about covering radius. I can give you 1,000 variations of this problem. A very interesting one is how do you distribute inimical dictators on the planet, a whole bunch of Hitlers. You don't want them to be very close to each other, right?
So this problem's solved? I mean, there's an analytical solution for that problem?
I will say, for which values of n? Very, very few. Okay? So I can immediately tell you, yes, that's being solved. For 1 through 14, when you have up to 14 points.
So n equals 2, they can do it.
Yeah, sure. And then for 24. So this is rigorous solutions. All right? More, maximal codes. Oh, I didn't say that. It was stuck down in the middle, but it's sort of important. This has relation to coding theory. So what happens with coding theory, you represent the information as strings of zeros and ones, right? And that is the so-called binary space. And you can consider the length to be that large length of strength n. And then you have 2 to the power n, different words, so to say. And, well, that gets really large. We know that exponentials grow really fast. So if you want to select a subset and you want it to be distributed well, you have to do it in a smart way. And that's the relation to these being called codes. Okay? And coding theory has, of course, many applications to information theory, to cryptography, etc. So, puffer fish and more orifices. And here comes nanotechnology. This is really the big splash done by the discovery of the Bucky balls in 1985. And that friend here is actually a 60 carbon atoms cage. And inside it has some metallic atom, and I don't know which one. But this is the interesting part about that molecule. It's spatial. You can hide things inside. You can hide medicine that fights cloths, for example, or cloths or something else, fool the brain and let the medicine go beyond the brain defenses because the brain thinks this is carbon. There are many other applications of the buckyballs. Unfortunately, I'm not into that part because it's really, really profitable. I'm more in the mathematical side of things and the theoretical. Wrong doctor. What can I say? Nanotechnology, they actually started growing these carbon molecules and growing them to very, very long in meters, maybe kilometers, etc. There are these speculations about space elevators. You place one big weight somewhere close to the moon, connect it with carbon ropes to the Earth, and then you can actually utilize the attraction of the moon to keep this steady and then just lift things, elevate things in the atmosphere. Any kind of science fiction, you name it. So, the discovery of the buckyballs. This is really cute and very interesting thing. So Kroto was studying intergalactic chains of carbons, and he was saying that they must have formed into interstellar atmosphere. And he wanted to imitate this, on Earth. And Smalley had that apparatus, laser beam, that was vaporizing metal atoms in his research, and it's called laser supersonic cluster beam apparatus, AP2 or something like that. So Curl was the connection between the two. He knew Kroto, and he was visiting Smalley in Riesz University, and he said, well, why not try to help Kroto out with our apparatus, because Kroto was interested in vaporizing graphite. But initially Smalley was not quite convinced, but then Exxon started doing these kinds of experiments, and Smalley said, well, maybe I should get on the wagon. So on September 1st, 1985, Kroto comes, rents an apartment, puts his luggage in, and starts to settle. They load the apparatus with graphite discs, and two graduate students, Heath and O'Brien, start doing the experiments. September 9, they discover a huge molecule, 720 atomic mass units. Now, carbon has 12 atomic mass units, one atom. So that suggests 60 atoms. And then, all of a sudden, they start to ponder, how do you arrange 60 atoms? It has to be spherical because it's very, very stable. So he was playing with Smalley was playing with some pentagons and hexagons. Very soon they figured out, well, I'm giving up things from my talk, so I'll skip. In any way, they actually developed the model. They predicted the model. September 13, they submit the paper to Nature. October 18, it gets accepted. November 14, it's published. How about the discovery? What a discovery this was. 1996, the three of them received the Nobel Prize in chemistry with honorable mention of the graduate students, of course. So this is the team with, you will guess, the soccer ball. And, come on, this is the paper, actually. Just 2 pages. I just copied the buckyball part of it just because it wouldn't fit the screen. So they named the molecule after Richard Buckminster Fuller, who was a great mind and great architect. This is actually the 1967 Montreal biosphere designed by him. You can see that cage, steel cage outside. That's actually this kind of spherical dome structures. And I did do my PhD in Florida, and of course I visited Epcot Center. How did I know that I'll end up doing these kinds of things for a living? But then some ancient Fullerenes. That's actually a Chinese statue that has under the lion paw exactly a soccer ball, and I'll give you a task in a little bit, maybe get back to that guy. And computational Fullerenes, Rob Womersley, who visited IPFW in December. Actually, this is 1,089 points and associated with them, the school districts. So what is the IPFW's Fullerene connection? Of course, the winner of that award 2 years ago or last year?
I think it was last year.
Last year. There we go. Of course, you can see the Bucky ball right here, right, Stephen? Yeah. Well, I didn't ask you for your permission to use this. Okay, there is upcoming IPFW Fullerene connection. That's actually a very interesting talk that my student Ling Si Wu will be presenting at the Student Research Symposium. Okay, so journey to Fullerene land. Let's see how we are on time. As I told you a little bit earlier, with every single electron, we can associate a nearest neighbor, so to say, cell. And that mathematically is written with this equation that the jth cell, say this guy, is all these x's on the sphere for which the distance to xj is smaller than the distance to all the others. So simple thing. And then we call such a guy soccer ball design. You can see it right here. Coming from Europe, of course, I call that football. And then this is a picture of 32 electrons at equilibrium, and these are the tiles of that soccer ball. And if you see, the vertices turn out to be exactly 60, and they turn out to be the atoms of the Bucky ball carbon 60. All right, soccer ball designs occur in nature frequently, and who knew carbon 60 can actually be found in nature in candle soot? They just didn't know to look for it. Well, once they knew about the molecule, they found it, of course. Soot. Yes. Did I say soup? It's written in it, but you don't see it. I know. So candle soot. We have this kind of miscommunication in the office very often, you know. What can I do? I can't get rid of the accent. But guess what students told me? That it's very cute. Not to use some more, you know, interesting words. Okay, so turns out there is a relationship, duality kind of relationship, duality structure. If you have 32 electrons, they're related to carbon 60, and here the faces actually indicate the number of electrons. The vertices indicate the number of atoms. Okay? 122 is related to 240. Carbon 240, which is an inert molecule, and I told Stephen that it actually exists. He wasn't aware. Oh, maybe you didn't care much about it. But in any case, it does exist. Maybe it doesn't interact with metals and other things, and it's not really possible to create new molecules what Professor Stevenson's research is about. So here's an interesting question that I got from the vice chancellor. He was dean at the time. I was given this lecture at the College of Arts and Sciences, the distinguished lecture, and the next morning he asked me, "Oh, Peter, you had 122 electrons. What is the carbon structure?" I didn't know it. I had to compute it mathematically and answer my dean very quickly. And we had a very nice mathematical exchange, all right? And he was very knowledgeable about it. Carl, kudos.
Are there any dualities in between those two?
Yes, of course. Did I
Are there
say
any
that?
numbers between 32, 122? and
Well,
60?
32 is carbon 60.
Right.
Maybe I didn't indicate it, so there should be an arrow here,
Right.
and there should be an arrow
No,
here.
but I'm saying that's
122, the dual structure is carbon 240.
Are there any between 32 and 122?
Oh yeah,
That have-
oh yeah.
that-
Well, you will have for any value. Some of these buckyballs may may exist. Like carbon 70 is another one that is very well, you know, it exists. It's stable. So that's a good question, though. When is it possible, for example, to have a hexagonal Fulerene? So for what values will you have Fullerenes? The answer is no. Gosh, here's the time when I had to ask for answers. So why not? So it's not possible to create a hexagonal soccer ball. Now, of course, we are making one assumption, namely that every vertex has 3 edges coming out. This is a serious assumption, but it's also a reasonable assumption, and that's what we call soccer ball design, that's what we call Fullerene cage, etc., etc. So Euler's formula, here comes the great Euler, faces plus vertices minus edges. If we have some polytope on the sphere, actually points on the sphere, you connect them and you form that, then you have to have a constant, and that's the characteristic for the sphere is 2. Okay? And F is the number of faces, V is the number of vertices, and D is the number of edges. So here's the cube. We have 6 faces, 8 vertices, that's 14, minus 12 edges is 2. The soccer ball actually turns out to have 32 faces, 60 vertices, and 90 edges. So 32 plus 60 minus 90 is 2. Well, suppose that we could tile the sphere with hexagons only. Okay? Then let's cut each edge into 2 pieces and count one edge towards the adjacent vertex, 1/2 edge. So there'll be twice the number of edges, and each vertex will own one of these 2 halves. So we will have the total number of half edges can be counted as twice the number of edges or 3 times the number of vertices, and these 2 quantities are equal. Very good. Now, when you see, if you count each face has 6 edges. Count one of the half towards that face, count the other towards the neighboring face. Okay? So then we have 6F equals to E. A very simple application of the Euler's formula, F plus V minus E, that's F plus V is actually 2F, and E is 3F, so that's precisely 0. All of a sudden, it's not 2. Here's an assumption that we did, and then we ended up with a contradiction. This method is called proof by contradiction. Okay? So what can I do? In mathematical talk, you are destined to be exposed to proofs. All right? And I did one. I'll do another one. You can see the frown on top right there. More proofs. Well, okay, so we can't do a hexagonal planet. We can't do a hexagonal design, soccer ball, whatever. Can we do it with some pentagons? And that's precisely what Smalley was asking. And how many would we need? Exactly 12. And we will have to modify things. Okay, remember, I had only hexagonal faces. Well, now I'll have pentagonal faces and hexagonal faces. Okay? So let Fp be the number of pentagonal faces, Fq be the number of hexagons, and then the number of faces will be the sum of the two. Okay? And the formula for the half edges belonging to a pentagon or hexagon, for that matter, is going to be 5 Fp minus 6 Fq equals 2e. Still, we have 3v equals to 2e. Now comes the big algebra part. All right, are you ready? So let's do it. F plus v minus e. F was the summation, Fp plus Fq, right? Now, from here, we can compute, since 3v, we can figure out 2e, we know, is Fp plus Fq. We can divide by 3, figure out how much v is. That's 1/3 this thing. And then we have to subtract the number of edges, but the number of edges from here we can compute as 1/2 of this quantity. So it's more or less simple thing. Then we tell our students in college algebra, well, we have to find common denominator. What's the common denominator of a 2 and a 3? That's 6. That means we multiply everything by 6. Okay? So we get to 6 times that quantity plus twice times that quantity minus 3 times that quantity. And that should give us 12. Okay, excellent. Guess what? The number of hexagons disappears. Well, that was 0. And 6Fq plus 12Fq minus 18Fq is 0Fq. So it disappears, and what stays is only 1Fp. So you can do it, but you got to have exactly 12 pentagons. Okay? Now, actually, at this point, I'll just back out just a little bit to the computational Fulerene, if I can find it quickly. There we go. Now, another interesting thing, they experimented in 2003-05 maybe. Initially, people thought, oh, you got to have 12 pentagons and everything else is hexagons, and that's what carbon molecules could be made of only. Well, but turns out that the energy is forcing the appearance of some heptagons, 7 gons. And the difference between 7 gons, actually between pentagons and 7 gons, will have to be, pentagons and heptagons, will have to be exactly 12. They discovered it by performing experiments where they were mixing some kind of oil and water, and then the one was attaching to the other, and they were forming large molecule-like structures. It wasn't a molecule, it was a physical process. But anyway, it turns out heptagons appear, and when computations did get, computers caught up with that computational algorithms, they were able to compute minimal energy for thousands of points, and then only heptagons appear. All right, that's done. The easy part of the talk, I'm going backwards. The easy part of the talk is done. So where are we now? We're right here. Apologize for that. My colleagues have to go to a mathematical meeting. For whatever reason, the MAA Indiana section meeting was today, and I didn't catch up with that when they asked me about the talk. So anyway, I thank them very much for coming. Now, Ron asked me about what are the known optimal S energy codes or points. This is actually the best packing. What is known in the best packing is 1 through 12, 13, 14, and 24. That's all there is. Now, remember I had a parameter S. That was sort of interesting. When S is 0, that's the so-called Smale's problem. Logarithmic points are known 2 to 6 and 12. There is actually a Mastodon theorem here involved for 5. I will tell you a little bit about it later. The Thomson problem, which is the problem arising from physics, what is known is 2 through 6 and 12 as well. So is 2 through 6 and 12 for the sum of distances you're trying to maximize it. This would be Fejes-Stolz, a great Hungarian geometer who asked this question. This would be Fejes-Stolz problem. So depending on S, we know sometimes more, sometimes less. But you can guess this is nothing, right? There's so many more opportunities, but we don't have rigorous proofs. Even in these cases, the recent proofs for 5 were computationally aided, computer-aided proofs. There is such a thing nowadays. It's no wonder that 2, 3, 4, and 6, and 12 actually work. They work for any energy. They are what we call universally optimal configurations. They have the 4 points. This is a tetrahedron, regular tetrahedron. 6 points, that's more or less this is 6 points north, south, and a square on the equator. Octahedron. Exactly, 8 sides. So 8 faces. So octahedron. Then for 12, that's the icosahedron. And these are special kinds. But another of the Platonic solids, the dodecahedron, actually doesn't work. Okay? It's not a minimal energy configuration. Even for 8, the cube is not. If you imagine a cube and you twist, all of a sudden you can get these 2 sides closer together and decrease the minimal increase the minimal distance. Okay? So that is making it not solvable. Actually, precisely the solution is when you twist 45 degrees and you get them closer so that you have the squares on top and bottom equal to the edges from that adjoin the 2 sides, then that's how you get the best packing for 8 points.
That's actually known in chemistry. There are distortions where the symmetry is broken and molecules take on a certain shape.
Right, and that's the reason that the symmetry is not the best guy always. Sometimes it is, sometimes it's not. And of course, the hexagonal symmetries in the soccer ball are very, very important, and that's the reason that actually carbon-60 is of this type. Now, here's actually the connection with the 5-point problem. 5-point problem is very interesting. There's only 5 points. Now, in chemistry, I think the model that they consider is that S to be about 6. Okay? So turns out that computationally at least we can prove that when S is bigger than some 15 point something value, actually a square pyramid is has lower energy. It's not the bipyramid here. All right? The Mastodon theorem, this is something, a result that two colleagues of mine, David Legg, the late David Legg, the chair of the math department before me, and Doug Townsend, who used to be a chair in the 90s, early 90s of the math department, and myself, the three of us managed to prove without computer that when you take 5 points and you maximize the product of all possible distances, the best configuration is North Pole, South Pole, and equilateral triangle on the equator. That's the bipyramid. Okay? Hao and Xiao recently proved the Fayet-Stokes problem for 5 points, and Schwartz proved the Fayet-Stokes problem, the Riesz problem for 1 and 2, and recently he actually expanded that to S being about 4. But they both, the other two results, actually utilize computer-aided proofs. All right? So this is Henry Cohn, one of the leaders at the moment in the field. Unfortunately, you can't really read well here. It is the Mastodon theorem. Okay, Dragnev, Legg, and Townsend. And like I said, Melnick et al., a fundamental seminal paper published in Canadian Journal of Chemistry or something like that, actually from 1977, they conjecture that the critical value where we switch from bipyramid to a square pyramid is 15.048, etc. But there is no proof of that fact. And we're still seeking for one. So in higher dimensions, I was able to generalize the result. So if we consider, say, the two-dimensional sphere, which is in R3, 5 points. So as D, we can, which is embedded in our D plus 1 dimensions. Then we have D plus 3 points. What I managed to prove is that either the configuration will be degenerate. That means that it will be, say, 5 points on a plane. That is regular pentagon in the 3D case. Or there will be a vertex, and all the other edges to all 4 other points will have to be equal. That is the square pyramid case. Or every vertex has to have a mirror-related image. What exactly does that mean? You have a vertex, here's the mirror partner, and the other 3 form a mirror. The other 3 points form a mirror. So these 2 are mirror images, okay? So this really is a bisector, perpendicular bisector. Now what happens with this, such configurations will have to have, one point will have a mirror-related guy, and then the other 3 will have to be all related together. Well, if they are all related together, it ends up being a regular simplex, or whatever we call it, which is, of course, equilateral triangle in the case of 3. So this will be equilateral triangle. Bingo! We get the bipyramid. All right? Comparing the 3 types of energies, I was able to establish this in the dimensions 4 and 5, the exact configurations. There is still trouble in higher dimensions. The problem becomes really complex. This is in American Mathematical Society Contemporary Mathematics edition, and it must have appeared already. So, backwards. Separations, that's another part of my results. So we don't want, see, the energy is forcing the points to stay away from each other. Now suppose we have 100 points, okay? The total area of the unit sphere, when the radius is 1, is 4 pi, okay? So now we expect to have the school district, so these small cells, to be about the size of 100 of the total area. Okay? So that would be that this minimal distance should be bounded below by the square root of 100, because every area, of course, is pretty much pi, we had a pi day recently, times r squared. That's the area of a circle. If you're close to a spherical cap, it's about the same. So these radii, pretty much how big the school district should be, they should behave like 1 over the square root of the number of points in the limit. That's what we call well-separated points. Well, it turned out that the well separation I have, that's when actually this part of my research started. It was first established for the logarithmic configurations by Rachmanov, Saf, and Zhao. Rachmanov and Saf were professors at University of South Florida, where I was. Saf was my dissertation advisor. And when Saf was on sabbatical, he asked Rachmanov to oversee me for that semester, and we actually started with my dissertation topic. So the problem for my dissertation topic was given by Rachmanov. But in any case, Zhao was another colleague of mine, graduate student, that was working on the spherical points. And it was really difficult subject, and deriving theorems there is a very tedious and difficult task. So when I had to make a decision, do I want to work on this project, on this problem that Rachmanov gave me, or do I want to work on minimizing energy of points on an ellipsoid? Now, I'm sure the ellipsoid would have been more profitable, but who knew? Maybe I wouldn't have gotten any results. So I stuck to my topic. Only later on in life, I started with minimizing energy on sphere and other manifolds. And that's actually the first result that I got. We were trying to work out the Mastodon theorem with Legge and Townsend at the moment, and I thought that if I can show that somehow they are separated, I'll be able to get my result. And I knew of that paper. I didn't know exactly how they proved it, so I reproved that separation result. Guess what? I made a mistake. So how did Rachmanov, Saf, Zhao prove their result? Well, they take endpoints, fix one on the south pole, and project from the north pole everything on the plane. How does a stereographical projection work? Imagine the sphere being transparent with the points being right there. And then you put a light source here on the North Pole, and you have a screen on the bottom. Then it will project the shadow of every point on that screen, right? So this actually introduces new points on the screen which minimize some kind of an energy. So they did that. They derived a separation constant of 3/5. The larger the separation constant, the better you are off. Well, only after I actually looked at this, what I did, my mistake was I picked a point to be at the North Pole and placed a light source there. But when you place a light source at the point, well, that point will spread out throughout infinity. Think about it this way. It's as if it exerts external field on the remaining n-1 points. Okay? So now I solved the problem for these n-1 points. Actually, I did one step further. I solved the problem for infinitely many points with that external field fixed, and I got some big circle that was I knew that these n-1 points were in that big circle. That big circle had a radius square root of n minus 1, n minus 2. Project back, that gives you a separation region. So this is pretty much the idea. Now I know I'm losing you, because this is getting into the nuts and bolts. But more or less, we did the same thing in 2007 with SAF, and we managed to establish the separation not only for the logarithmic, but also for any energy. So we completed, exhausted, so to say, the separation property. Then later on, because I did already consider that external field in the logarithmic case, we said, well, now let's consider in general, and that started another whole section of my research that is related to discrete minimal energy points with external fields. And the key idea was that the Q optimal point, so imagine that minimizing energy with external field, and everything has external field. We have gravity potential on Earth. We can't just ignore it. So this is external field to any kind of experiments that we do. All right? And there may be electromagnetic field. There may be other things that affect minimizing energy. So what is important is that the discrete solution is contained in the so-called continuous solution. Remember when I said that I actually solved the problem with many, many points? I solved the continuous energy problem. Now, I'll leave the boring details of this and maybe tell you this one. This is nice, okay? And I will be able to explain it. So here's a sphere. And think of it as you pre-charged the sphere. How do you do that? You ground the sphere. Well, that's not a very good sphere. That's a distorted sphere, but that's fine. You ground the sphere with a cable or something. Introduce some positive charge that, well, I want to run the negative, so most probably introduce a negative charge so that it runs the electrons down to the ground with some unit, okay? And then I disconnect the cable. The sphere now is insulated and it has lack of electrons. Oh, well, maybe I did want to introduce positive charge. I don't know, doesn't matter. So now the sphere has something, certain charge, right? Let's think that it's positive. And then I start introducing, well, let's make it red, a different color. Start introducing this charge again. So we have +1 here and +1 here. And what will happen, it will repel the positive part. Initially, the positive charge is uniformly spread over the sphere, right? But as you move this guy, you will introduce more and more positive force, which will repel the positive parts here. Negative will come in, and at one particular point, a negatively charged pole will appear. Okay? So the question is, what is this critical place? All right? And I was given this talk at Vanderbilt. There was a Russian professor from the Keldysh Institute in Moscow visiting there. He's actually the director. And he asked me, Peter, what is this number? I told him, well, I don't know. It's some number. No, Peter, I want to know. Coulomb forces, unit charges, unit sphere. Tell me the number. Well, I gave my lecture. We went to the home, and we were supposed to go out to dinner. And what I did is I computed quickly the number. It's the golden ratio. Well, wait a minute. I think I screwed that up. Well, no, that's it. That's it. So it is amazing. And here at SAF, my host and Sasha Tekarev were sitting in Longhorn, and I pulled out a napkin, drew the picture, showed them this. They said, can't be. This is too good to be true. I said, well, it is. Anyway. So this brought a whole other slew of several papers devoted to the subject. Brocher, myself, and that staff actually have the separation of Q faculty points, so the external field points. That's a new result. In potential theory, the flagship journal in potential theory. And then this is something that I usually call that my Pacific crossing theorem. It's still work in progress. We tabled sort of this project, although it's a very, very good project, but the other one that I'll show you later is much larger. Anyway, here's what's going on in the particular case of a logarithmic external field. And this is work in progress. And what is really interesting, it has applications to log gases. That is a very, very hot subject in statistical physics at the moment. So here's what the issue is. Think that we have placed some points. These are external fields. We fixed their mass. And we start to introduce more and more positively charged particles that interact. Then these guys, depending on, for at least small values of these charges, I will be able to solve explicitly the problem. And what will happen is we will have these, the red dots, uniformly distributed. Okay? And I'll know precisely what are the circles. This is for two guys. Now, that's up to where I can do it. Once they start intersecting, it's not working. This is for three. So I was visiting Brochert actually in Sydney, and was talking to Rob Womersley, and I said, well, Johan and Rob, these should be precise circles or spherical caps. They said, no way. That's impossible. Then Rob actually, oh no, I moved. Rob actually did these pictures, computed, and as I was flying back, sent them in cyberspace. But it's a long flight. It's 15 hours. From Sydney, well, on the way back actually shorter, to Los Angeles, 13 and a half. And I got tired of watching movies, so I said, I gotta work on that. I actually managed to prove this. Okay, so it's another theorem done in the middle of the night on 10,000 meters or 30,000 feet over the Pacific coast, Pacific Ocean actually. Well, I may have finished the theorem when we were in the Pacific coast. So this is actually the big project that tabled that previous project. Well, we're working on it, but we'll get the paper this year. But this is something that started with international agreement that we have with Sofia University and Bulgarian Academy of Science. There's 5-author team, Boyvalenkov, Professor Boyvalenkov, Peter Boyvalenkov from the Academy of Sciences in Bulgaria, myself, Hardin and Saf from Vanderbilt University, and Stoyanova from University of Sofia, my alma mater back in Bulgaria. So the paper just appeared in the flagship journal of approximation theory. So what we actually managed to do, now this is for, remember when I told you about these universally optimal points, the 1, 2, 3, 4, 6, and 12? Well, we find a lower bound on energy that is independent of the potential, in some sense, interacting potential, that exactly matches for these universally optimal points. It's really, really good. And it's like a brand new thing, and we don't know what the full extent of this discovery will be. But this is the energy. Big N is the number of points. Little n is actually the dimension where the sphere is in. So you can think of regular 3 here. And these are some numbers, real numbers between -1 and 1. They have something to do with mathematical analysis. It's called quadrature, formulas, etc., etc. We could compute these potential interactions at these numbers with certain weights, and we get that bound. Now, that may not seem very impressive to you. It seems really impressive to me and many other mathematicians. Now, I was a plenary speaker at the Vienna Erwin Schrödinger Institute in Mathematical Physics, International Institute in Mathematical Physics, and this was my, when I showed that slide, it was, oh. So, this is actually Henry Cohn, that same guy, and Abhinav Kumar in a groundbreaking paper from 2007. They have a list of all these universally optimal configurations. All of them are so-called sharp codes, except one particular guy. This is the 600 cell guy, some special guy. So our bound coincides for all of these. We actually get exactness of the solution with our bound. Now, unfortunately, we already discovered their optimal configurations, but imagine that these are certain points, okay? What we did is connect the lines, the line passing through the points. So this is the magnitude of our own theorem. And here's I illustrated. See, this is when n's dimension is 4. So S3 is a very special unit sphere. X squared plus y squared plus z squared plus w squared is equal to 1. You have 4 coordinates. And in that guy with 24 points, that's also a very special number, you can find actually it's a solution. We explicitly derive a solution. It's called linear programming solution for, it's a polynomial solution for various potentials. And these are these real numbers that I was telling you about. You compute them, there's 3 of them. In this particular case, that they depend on the dimension and the number of points. That's all they depend on. You derive these numbers, and all you do is consider the interaction and plug in these numbers and compute your formula, wrong direction, right here. Okay, so knowing these and knowing these, all I have to put in the potential. And depending on the potential, we get the bound. Now, how good is that bound? Well, here's a comparison. This is, again, 4 dimension. What you see is 5, 6, 7, 8, 9, 10 points, all the way to 64 points, with the harmonic energy, which is the minimal energy in the harmonic case or the Newton case. Okay? And here's our bound, ULB bound. Now, the ULB bound is supposed to be smaller because it's a lower bound. And what it is, this is the percent of error. As you can see, we go down to a 0.2% of error for 64 points. That's big. Okay? But when you consider interaction that is a Gaussian interaction, all of a sudden you now get to a 0.002% on only 64 points. So this is how good that particular guy is. And then we are, well, that's actually, I wrote 2015. That's still, some of it is submitted. The Croucher points we're waiting to hear back. And then these are the projective spaces, and more work to be done, future work, is there are Johnson polynomials, asymptotics, etc., subintervals, higher degree polynomials, you name it. So far we have 2 conference and 3 journal papers out of this, with at least that many projects in the works. So yeah, that tabled our Pacific theorem, but not for long. So this is the team, and this is my team on external field problems. This is Johan Brohart. He visited us last year, and I expect to see him this summer, either in Bulgaria or in Austria, where he's now. He used to be in Australia, but now he's in Austria. This is another set of my recent results that I didn't have time to talk about, and that was sort of like related. But this is Tatik from University of South Florida and Hungarian Academy of Science, the youngest academician in the Hungarian Academy of Science anytime elected. Now, this is now. He was elected maybe 15 years ago or something like that. But this is big. For the Hungarian Academy of Sciences, mathematics, this is huge. And this is Professor David Benko, who is visiting us from University of South Alabama now. So we've done some work on convexity of harmonic densities, etc. And finally, the team from the Mastodon theorem with Maynard Mansfield, who was the founding department chair of the math department here. Actually, this was all chairs of the math department minus Ray Pippert. The Pippert Award is devoted to him. And thank you. Yes.
So all the potentials that you have are classical potentials, and you have a number of applications. But since many of us are interested in
Lennard-Jones potential?
No, I was thinking quantum mechanics, actually.
Oh.
And since you spoke at the Schrödinger Institute,
Yes.
you know, how daunting a task would it be to
Very
deal-
daunting, but it is getting there. It actually is getting there. And what we've done, all right, when I said general potentials over there for that lower bound is actually for absolutely continuous potentials. What is an absolutely continuous potential? It is a function potential that is on the inner product of the points. When you have points on the sphere, you can introduce inner product in higher dimensions. Dot product is what we call it in multivariate calculus, for those of you that have taken that thing. But it's the length of one vector with the length of the other vector times the cosine of the angle in between them. That's what a dot product is. So then this, all of its derivatives have to be positive. This is the kind of absolute potentials that we consider. Now, when you get to quantum mechanics, I'm scared getting there, because things exist and they don't. But the good news is the statistical interactions are predictable. So really, I suspect there will be ways to handle that.
You also can get into non-local potentials.
Well, yeah, the Lennard-Jones potential is really, really a good one. Very hard to get to do. So 1 over r to a power s is the potentials that we consider. These are called Riesz potentials. The Lennard-Jones potentials, they are like that. Well, you can introduce some constants if you want. And then what it looks like is, well, maybe something like that. That's what it looks like. It's very different from this kind. And they have a near-term interaction, blowing up, and a long-term interaction. Okay? And here in the long term, they look like that. So little is done.
But that has a lot of implications for chemical bonding.
Oh, yeah, absolutely.
You forgot to give the audience your little quiz. Lion's paw and the.
Oh, yeah. So this is obviously a hexagonal design. Where are the pentagons?
On the other side.
No, there is one right here. But, you know, it's interesting to actually browse over. This is a pentagon, right? And the fact of the matter is that there have to be 12 of them. That is fascinating.
It just shows that they couldn't do it without.
Exactly.